This is Steven, and today we're going to talk about lowering the power. So, I had a situation at work that involved bloody pull-down resistor and how they were sizing it. So I solved it, but then it got me to thinking. I always just did 10K for the heck of it. No rhyme or reason, I just did it because all the old designs did it. If I cared about battery life, we might do 100K. Maybe a little bit more for feeling lucky. And it just hit me. I never figured out how to size these things properly. I've just been doing whatever willy-nilly. And because of that, I'm probably using values that are way lower than what I have to, which means I'm wasting power. And in my designs, the setup you see here, I often have way more than just one. 5, 6, 10, maybe even a little bit more. So if I'm using 10K and then you gotta multiply this by 10, because that's how many I have, this starts to become non-trivial. So I wanted to look at how did we even get to 10K in the first place, and how high can we go? The first thing we want to do is look at all the currents that are coming into and out of this pin. That will help us figure out why we can get away with 10K and what values we can go up to. Second thing we also got to know is our threshold voltage, the minimum threshold voltage. So we're going to go through all that. So let me switch over to my fancy spreadsheet. Now there's kind of a lot to go on here. I will step you through this. Do not worry. No panicking. First thing is gate-induced drain leakage. You only hear about this in semiconductor textbooks. So this is when your gate is low and your drain is high. Not necessarily, I'm not talking digital low or digital high, I'm talking just the voltage level. So we're going to put in about 10 nanoamps there. You will never find this in a data sheet, but I'm still going to put a little in there to just tell myself, hey, it's there and I'm accounting for it. Now, our next item that is in the data sheet is gate to source leakage. So with the MOSFET I have chosen to analyze, which is this 2N7002K, what we have here is back-to-back diodes for ESD protection. And that happens to look something like this on the graph. This is normalized, so your x-axis is VGS, and then here is a normalized graph. So if I'm here, the next line is 10 times higher. So that's why we get numbers here where if we're at the edge, we're at 10 microamps, and then bottom, much, much less. So I had to get this from a Texas Instruments white paper because nobody seems to graph this. So this graph here is not of this 2N7002K. So this is just to give me a model, an idea of what it's supposed to look like. So if you do not have those back-to-back diodes, it will look a lot different. I would encourage you, put this into Google because it's kind of nice. Now you might notice I'm not accounting for it. Otherwise, I would have put minus 150 because it's flowing from gate to source, so it's flowing out. So I'm putting this at 0. 1, to give me a bit of a safety margin. 2, I don't want to have to spec this every time I look up a freaking MOSFET. What if I have a supply issue on it, man, and I gotta find a different one and approve it in my job, and no. Or just think about the next guy. Do I want to make him do this? No, for all I know, it's going to be some new guy that frankly doesn't know much, which is fine. But I just am thinking about the next person and don't want to make this a big deal for them. So the next thing on the list is the I/O pin leakage on a microcontroller. So I just picked a random microcontroller, looked through the data sheet, and this is what I got here. So these bottom two here, you can ignore. It's just this top one we need. So it's 150 nanoamps. That's a maximum value. They don't give low and they don't give typical. So I got to use what I got. In the real world, with how we're doing this, I bet it's a lot lower, but I don't know it. So I'm just going to have to use the number that I have. So also keep in mind, we're dealing with worst case here. So my microcontroller pin is going to be configured as an output, but not all the time. What if that reset pin is triggered? What if I'm programming the microcontroller? What if at initial power up, it's going to take microseconds, nanoseconds. It's going to take whatever time it is to configure that pin as an output. So in those scenarios, this is an input or high Z, high impedance. So this must be accounted for. Another item that must be accounted for, and they ain't going to teach you this in school. It's called surface insulation resistance. So if you have a board that's low humidity and it's clean, this number, your resistance here, along with the voltage, is going to get you in picoamps. But that high humidity can really mess up resistance on the board itself. And pins and all this. This is why your ICs are, when they're packaged, it's low humidity. And they'll give you humidity specs. Like when you open this package, like you got 30 days to put it on or something like that. So I would encourage you to look this up. This is a way bigger deal than I ever thought. Like I was never taught this. So, but we're going to use pretty much worst case here. So noise, this is a crap ton, but I just did this to get close to 10K as kind of a what if. Like this is nuts. That's a lot. Now, our desired gate voltage here. This one was kind of interesting. So if we go in here to the data sheet, we scroll down to where we get to threshold voltage, we get these two lines right here. So we have a minimum here, then we have a maximum here. I do not want accidental turn-ons in any scenario. So I will be working with the minimum number. Now, we have a negative threshold temperature coefficient. A lot of words. That means, I wish they would have put the negative sign here, but I guess they used the negative word right there. So let me show you the graph. We scroll down, we are right here. Threshold voltage with temperature. And at 25 degrees C, they just went at 2 volts. But as you can see, as junction temperature rises, the threshold voltage goes down. Kind of a lot. So if we go back up here and do our math, what I did is I just assumed max junction temperature to get the absolute positively worst case scenario. So that gets us to 0.5 volts. So with all of this, yeah, your 10K resistor is going to work no matter what. So, and I think part of this noise also is bad layout practices. They've been using 10K since the 80s. So 40 years ago, our components were nowhere near as good. Surface mount wasn't really yet. Was it even the thing back then? Doubt it. Ground planes, for what you were doing back in those days, they may not have done ground planes back in those days. 2-layer boards were way more common than they are nowadays. So I always liked 4, but back then, probably would have been a lot more expensive than it is today. So this accounts for a lot, not to mention compliance issues with, stricter requirements today than what they had back then. So this accounts for a lot. Okay, now that I have an idea of just, okay, I threw everything I got at this, and the 10K still seems to work. Okay, now what can we do? Okay, so what we can do here is, you know what? For the products that I do, I just can't just wave my hand and say low humidity. Some of these are pourable. They will be used in high humidity environments. I can't do anything about that. The dirty surface, though, yeah, I can. Some of you cannot. Like the computer I'm using, it's got fans. Eventually, it's gonna get dirty on the inside. Hopefully, it takes years, but we've all cracked open some piece of equipment and there's a ton of dust in there. But for the here and now, we're not going to deal with that. So we're going to assume this is 0.0033. Is that nanoamps? Yeah, much more reasonable. And you know what? We're not maxing this bloody gate voltage out. So let's just assume we could, we'll put a little bit of give in there. Let's go to like 0.8 volts. That's still below our minimum. Okay, so now we've gone to approximately 20K ohms. Big freaking deal. But what if we could get this noise to, we could just zero it out. Whoa. That's a big difference right there. We're almost at 5 mega ohms. What? I've been using 100Ks for like a new design. And the math is telling me that if I can handle this noise thing, we can go not only up, but way up. Instead of this 330 microamp business, we can get it under 1. Might as well be calling it nanoamps at that point. So, hell yeah, if we can make this work, I'm in. So let's do this. All right, back to the schematic. First thing we need to do is change this to our new value. Oh, that feels good. Okay, now we're gonna recompute this number so I can feel good. So let's open my damn calculator. 3.3 divided by 4.7. Oh man. Damn. 0.7 microamp. Super high. Don't think so. Super awesome. Now we're going to put this down here. All right. Now, let's put on our thinking caps for a second. Resistors are pretty good at sinking DC currents, but there's another thing that can handle higher frequencies. Capacitor, baby. Load that. Load it. Give me that cap. And hurry up. I can't wait. My noise has got to go. Okay. Capacitors. What intonation? Let's go with... Yes. Yes. Hey. Go. No. Get out. Don't you argue with me. Man, KiCad is just... It's a thing. Just put it that way. Okay. So, now we got our capacitor here. What are we going to do? 10... Whoa! Caps lock is on. 10 nanofarads. It's kind of a lot. First thing you're going to say is, well, that's going to slow this down quite a lot. Yes, it is. As a designer, you're going to have to take that into account in your design. For most, it'll be fine. Now, if you've got high current going here, you're going to need to look at your safe operating area in your MOSFET's data sheet. But since I've got only a few milliamps, we good. And whatever this is doing in this case, I really don't care how long of a turn on time this is. It's not the end of the world. Okay, second thing we need to do now is we need to add another resistor. So give me an R. Then give me, I don't want a variable, give me a resistor. We're gonna go US, USA. Okay, we're gonna go right here. Oh my God. I'll get this. Okay, there we go. No, get out. Okay. What are we gonna... See, I'm a little used to Altium and how it does things. KiCad, it's free. What are we gonna put this as? Well, this serves a few purposes. One, it's gonna form a low-pass filter. Two, this is gonna... What I like doing, I like gate resistors no matter what, to limit the current going into the MOSFET, just to ensure that we're not going over any kind of maximum limit or anything like that, because I want my design to last forever. So we can go something like 200. So this is going to form a low-pass filter right here. So another thing we got to do is, in the layout, we need to have all these close. So we're going to put it nearby. So this is kind of a hint to myself, or if somebody else is doing a layout, hint to them that all this needs to be close. Because you've got a crap ton, and I mean potentially a crap ton of inductance on this. So any noise that couples on here, it's going to go through that inductance. It's going to raise all that voltage, and it's just more for this to sink. So another thing we need to do, let's assume this is a long trace. This kind of works as a termination resistor also, but what can help is if we do one that's physically close to here, as well as this one that's physically close to here. So this noise issue also is why we cannot use an internal pull up or deal with like a pull down. Because what's going on is that, let's say noise goes here. Well, by the time it gets over here, because of impedance, remember that formula is 2 pi times the frequency times the inductance. So at, say, like 100 kilohertz, you know, it doesn't take that much inductance at all. Parasitic inductance, that'll make this huge. So we just can't rely on any kind of like pull up or pull down here. We got to do it near here. That way we can knock out all this noise and it all just goes to the right place where it's supposed to, which is not into the freaking gate so it accidentally turns on. Now, this is only, the schematic is only half the battle. The other half is, how do I do with the layout. So let's start with basics. Obviously, I would hope at this point, surface mount. 2, these need to be very close to the gate. So I want you to think of it, because really what we're doing here is, this is a decoupling capacitor, because we're decoupling the inductance from the rest of the circuit to minimize all this. The only difference is between what we would do for this gate versus the microcontroller is that we're not using it for like local power storage or something like that. So no, I just need this to knock out these higher frequency signals to get rid of the noise. Also, good design, make this trace as wide as you can, make it short. But if you can't, you can't. Sometimes I gotta have these over a foot long. That's over 30 centimeters for the metric people. So there's other things you gotta do. So layout guidelines. All right, 1, SMT surface mount components. 2, proper component placement. 3, this is going to sound basic, but we got to say it. Use ground planes in adjacent layer. Now 4, if you can, use a 4-layer board. Keep that right there. Okay, there's also another one that I do want to mention. So this is the high frequency line. We want to get rid of as much of this noise as possible. Now, most of your designs aren't just going to have one line. It's going to have all kinds of traces every which way coming over. Who knows what's going on in them? Could be PWM or just other high frequency stuff going on here. Could have motors on this board, could have every which thing. We don't know what environment this thing is going to be in. Could be in an industrial environment with all the inductive loads happening, all the motors. So this is extremely aggressive for a pull down. So we're going to add a number 5. Stitching vias on trace. So very aggressive, but the power savings are there. And look, all we did was add 3 components, all of which are very cheap. You know, if you're doing BOM consolidation, you're using a 1K elsewhere, just use that here also. But you'll be affecting your RC time constant. But as a designer, you got to know all that stuff anyways. So stitching vias, put them 100 mils apart, 0.1 inches, all along here on both sides. It's kind of like an RF circuit. So basically what you're doing is making a Faraday cage around this trace. That way noise cannot get in. Oh. I was looking up, back in the 1980s, doing vias, yeah, you can do them, of course. But you couldn't do them willy-nilly back in the day. Nowadays, we can put hundreds in and nobody will bat an eye. Back then, you really couldn't. So do the stitching vias. Now, another thing I would like to mention is that AI is great. It really helped with the math. So instead of me having to hand calculate everything or put it on a spreadsheet or whatever, I could just say, hey, I want this. Do the math. And then it did the math. Then I could look at it and say, okay, that looks good, or it doesn't look good. Or it could give me its opinion. Now, is it always right? No. But I found it right enough of the time that it just speeds up the work so much. I would encourage you, use AI. It will help you. Is it perfect? No. So in general, this is how you want to do it. This is a low noise design, and I think, listen, if you want better battery life, you got to do one of two things. Get a bigger battery and incur all that cost, or decrease the current that your device is using. So because this costs pennies, along with the time to do a good layout, I think this is probably where we're heading, of using higher values. So I am very interested to see if this actually works in real life. I would have never dreamed that you could do something like this and potentially get away with it. I thought maybe 1 meg. 1 mega ohm might be pushing. I thought 100K might even be kind of aggressive, but with our modern techniques, it's probably okay. I had no idea we could even conceivably go up this high. So I kind of want to test this. So we'll see if I can get a board made and going on with something. What I probably would do is get some PWM going on right near these traces and see what can go on. And yeah. So I want to thank you for watching. And I would encourage you to challenge assumptions that others are making. Because the assumption is that 10K is the bee's knees. Well, it's not anymore. And we got to open our mind to being able to do things a little bit differently than how we have. So thank you for watching. Goodbye.